Cauchy Y, also all about solving Diophantine equations.
Thank you. Can everybody hear me? So before beginning, I would like to thank the organizers for having invited me here. I would also like to thank the staff for helping me through the numerous hassles that an alien needs to go through before arriving in the US. So, my title is pretty ambitious. I'd like to talk about explicit methods for solving Diophantine equations. Now, is there a problem? Oh, thanks. I had two ways of doing this series of talks. One was to give a survey of the innumerable methods for solving Diophantine equations, and the second was to focus specifically on one of them and explain it in all its technical details. I chose the first solution because I think it appeals to many more people. And also, I gave as a student project one of the most beautiful, I think, aspects of this, although it's now pretty old, which is the use of the Heegner point method to find rational points on elliptic curves of rank 1. So what you're going to hear is a quite wide survey of Diophantine equations, and I apologize in advance for two facts. First of all, it's going to be at a level which is quite, well, elementary in some sense. And second, I'm not going to include many proofs, because I think giving proofs on slides is maybe not so helpful. I have put a complete text on the web, including, in fact, a 200-page extract of a big book which I'm publishing with Springer. The full book is here. It's almost 1,200 pages. And feel free, I mean, I would be very happy if it's in four half volumes here. I'd be very happy if you could take a look at it and make any sorts of comments on this. So let us start. So I'll start by giving some examples. I have to read here because my laptop doesn't work very well. So as you all know, a Diophantine equation is a system of polynomial equations to be solved either in integers or in rational numbers or more general number rings, whatever that is. It can be in function fields. It can be probably the most famous, even though it's not the oldest, is Fermat's last theorem. So I just give three examples of Diophantine equations. So Fermat's last theorem in Z, x to the n plus y to the n equals z to the n with n greater or equal to 3. Fermat claimed that this was not possible with x, y, and z non-zero. And I believe that all historians of mathematics agree to saying that this was a single equation which gave the impetus for the creation of algebraic number theory by lots of people, of course, starting with people like Kummer and Dirichlet and so on. So these methods were able to solve Fermat's last theorem up to quite large values of n. I don't know what the record is. Of course, this has become obsolete with the work of Wiles, but they went certainly to several million. The second result, which was found, well, it wasn't directly linked to Fermat, but it had immediate application, was Falting's results on rational points on higher genus curves, which proved that for fixed n, only a finite number of coprime solutions could exist. This, of course, didn't prove that there was only a finite number of solutions when you let n vary, but at least for a fixed n, because it's a curve of higher genus for n greater or equal to 4. And as you know, it was finally completely solved using elliptic curves, modular forms, Galois representations, and so on by Ribbett-Wiles and Taylor-Wiles. And the method that they used in the modularity conjecture proved by Wiles, Taylor, Wiles, and successors is certainly much more important than Fermat's last theorem itself. But as quite frequently happens in Diophantine equations, the tools that are created to solve the equations are very often much more important than the equation that you solve with them. In fact, I think that's true for number theory in general. I mean, number theory has quite a special place in mathematics in that it helps, it provokes the creation of tools to solve number theoretical problems, and it's quite interesting in a sense. Perhaps number theory is the only scientific part of mathematics, because one discovers secrets of nature, while the rest of mathematics is tools which can be used in number theory and in other places, of course. Second example is Catalan's conjecture. And that's quite an interesting example because this equation is very closely related to Fermat. It says that if m and n are at least 2, not 3 this time, the only non-zero solutions to x to the m minus y to the n equal 1 come from 9 minus 8 equal 1. And what's quite interesting is that the methods which were used for FLT, of course, apply to Catalan. You can use class number things, I mean, non-divisibility of class numbers of cyclotomic fields to show that this equation doesn't have solutions for given m and n and so on. And using algebraic number theory, it was possible to solve quite a number of cases. And so this was quite similar. Then the next progress, a little analogous to Falting's progress, was remarkable work by Tiedemann, who showed that the total number of solutions, you don't only fix m and n, you allow m, n, x, and y to vary. The total number of solutions is finite, and this is not at all by using Falting's type results, but by using Baker's theory of linear forms in logarithms of algebraic numbers. And this was quite an interesting result, especially since Baker's theory, as you probably know, is effective, meaning that you can really give a bound for all these quantities. It's quite an interesting fact that the bounds that are given by Baker, well, this is not on my slide, but the bounds that are given by Baker's theory are usually absolutely huge. I mean, 10 to the 10 to the sometimes doubly exponential like that. But it's also a very interesting fact that in most cases, there are reduction methods, which are either continued fractions, LLL, or this kind of thing, which allow you to descend these bounds to much more reasonable numbers. You can descend from 10 to the 10 to 10, but not in the case of Catalan's equation. The results of Tiedemann were not sufficient to put what remains on a computer. And the final step, and that was a big surprise, was taken by Mihailescu, Preda Mihailescu. Well, he started in 1998, if I remember well, but the final proof was in 2001. And it's very interesting because contrary to the proof of FLT, he didn't use any, well, I shouldn't use the word sophisticated because it's quite sophisticated, but he really used only the theory of cyclotomic fields. No modular forms, no level lowering, just the theory of cyclotomic fields, but he really needed a rather deep result in that subject, which is Thane's theorem, which those of you who know about it, of course, was also extremely important in the work of Kolyvagin, Rubin, and others on the Birch and Swinnerton-Dyer conjecture in rank 0 in one case. So it has other applications than Diophantine equations. But it's quite surprising that you can really completely solve Catalan's equation without any computer work at all, using only the theory of cyclotomic fields. So that's an absolutely beautiful proof, which I include, in fact, completely in my book for those of you who are interested. I just copied the notes of René Schoff and Yuri Bilou and with help of other people. So, in fact, incidentally, I would like to thank René, if he's in the room, for his help. So the proof was later simplified by Bilou and Hendrik Lenstra. So that's quite a different, but it's quite interesting that it was solved Okay, the third example is also quite famous, and that's probably the oldest of all Diophantine equations which isn't completely solved to this day. Since it dates to the Greeks, to the Diophantus of Alexandria, which I think is something like 4th century AD. It's the congruent number problem, which is to find all integers. Well, you can put rational numbers, but you can multiply by a square, so it doesn't really matter. So square-free integers, if you want, which are equal to the area of a Pythagorean, well, my pronunciation is awful, triangle, well, you can read, with all sides rational. So typically 3, 4, 5 is the simplest example. That has area 6. You can find a slightly more complicated example which has area 5. But you cannot find examples with area 1, 2, and 3. And 4, because 4 and 1 are the same. So 1, 2, and 3 are not congruent numbers. 5 and 6 are, and 7. So give a criterion for a number to be congruent. That's quite an interesting problem, essentially because of the methods which are used. So it's exactly equivalent to the solution, that's a trivial exercise, the existence of non-trivial rational solutions on the elliptic curve y squared equal x cubed minus x squared n squared x with y different from 0. And again, there were three stages in the solubility of this Diophantine equation. The first was essentially experimental work. For a given n, you can work out whether n is congruent or not, although it's not always that easy to prove a number non-congruent. So that was the situation until the mid-70s. Then came the Birch-Swinnerton-Dyer conjecture, to which, of course, I will come back in two lectures. This was quite a very nice thing, because if you want to know whether an elliptic curve, at least conjecturally, if you want to know whether an elliptic curve has non-zero rank, which is what this means, in fact, you simply compute the value of its L function at 1. That's what the Birch-Swinnerton-Dyer conjecture says. And if it seems to be close to 0, well, it's probably true that your curve has rank at least 1. And of course, that's one thing that I repeat to my students when they first learn computer algebra. Unless there is good reason to be able to prove that a number is 0, for instance, if the sign of the functional equation of the elliptic curve is -1, excuse me, I'm talking about things maybe you don't know about, but if you do, good. If the sign of the functional equation is -1, then you know, of course, that the value at 1 is equal to 0. So according to BSD, then you know there is an infinite number of solutions. You know the number n is congruent. On the other hand, if the sign is +1, well, you make a computer calculation, and computer calculations of, on elliptic curves of this type is really extremely simple. I mean, the programs are a few lines long. And you find that the value at 1 is equal to 0 to 1,000 decimals if you want. I mean, this just takes a few seconds. So what? I mean, it's quite... I think that computer scientists call this the problem of the zero. There is a name. Well, anyway. You cannot prove that a number is equal to 0, even though you compute it to thousands of decimals. And that's, of course, the main difficulty. On the other hand, even if you cannot prove it, you can be convinced that it's equal to 0. And then, if you see that it's not equal to the 0, that you can prove. You can always prove that a number is non-zero. You cannot prove that it's equal to 0. So if you know that if you can prove that it's not equal to 0, and you believe BSD, then there's no problem. You know that n is not congruent. On the other hand, if it looks like it's equal to 0, then your only hope, essentially, is just to look for solutions for points on the elliptic curve. Of course, you can use additional material to help on this search, not just do it stupidly. But in a sense, BSD gave a complete answer, although it involved analytic computations. But the final, although not quite ultimate, fact on on the congruent number problem came from a beautiful theorem of Tunnel using modular forms of half-integral weight, which gave, in fact, an algebraic criterion, not an analytic criterion, to check whether a number n is congruent. This just can be expressed in terms of quadratic forms in 3 variables. It's very easy to state. If you want the precise statement, look at my notes. Unfortunately, you still need a very weak form of the Bircham-Swinnerton-Dyer conjecture. So the problem, you can say, is essentially completely solved, except that, of course, we need somebody to prove BSD for us, which is probably one of the major problems in mathematics in the 21st century. In my opinion, it's probably the most beautiful, but that's my opinion. So let's look at the tools available to solve Diophantine equations. It's essentially impossible to classify because, well, you know there is a theorem which tells you that there is no algorithm to solve a Diophantine equation. You cannot write a computer program which will solve Diophantine equations. So, in effect, there are as many tools as there are Diophantine equations. But we can still try some attempt at classification. The simplest tools is certainly the local methods. So either you use simple congruences mod p or mod p squared, or more generally you use p-adic fields. You can use them either in an elementary way, just looking at congruences modulo powers of p, as I just said. You can use them in a slightly less elementary way by using theorems like Strassman's theorem or the Weierstrass preparation theorem, p-adic power series, and methods due to Skolem and Herbrand and so on. It's a little more subtle than simply using congruences modulo p to the k, because essentially the problem with congruences modulo p to the k is that you work in rings or fields with non-zero characteristic, and that's quite annoying. On the other hand, the advantage of qp or zp is that it has characteristic 0. So you can do things which you could not do otherwise, and you can, in addition, they have a nice topology, and you can do analysis on them. So this gives you really extra material to work with. Anyway, local methods, I will come back, of course, to this at length in a few minutes. But you can say that local methods are quite well understood. In fact, I would say almost completely understood. I could probably even remove the word almost. And are completely algorithmic. I mean, maybe I'm stretching my luck. But really, testing that an equation is locally solvable, probably somebody has written something about this, but I would say that this is essentially algorithmic. Okay, the second tool one can use is quite naive, and that was one of the first tools certainly used by number theorists in the Middle Ages or before, is factorization over Z, simply. It doesn't look very powerful. I mean, you just write, for instance, well, I don't know. If you want to factor a number, I think Dan Bernstein is going to explain to us how you do this. Well, you just write x squared minus y squared equals x minus y times x plus y. And I think that all factoring methods are based on this identity. Is that true, Dan?
Well, maybe a slight oversimplification.
Still. Even though the method is not very powerful, sometimes it gives quite spectacular results, which in fact sometimes are forgotten. For instance, Vent's criterion for the first case of Fermat's last theorem, which I will, probably that's about the only proof I'm going to give today, and Kessel's results on Catalan's equation. It's quite surprising. And the next tools, so 3 classes of tools which are usable. Factorization over number fields. That's certainly the biggest part by far of the tools which have been used. Of course, all this is very classical since it dates from the time of Kummer and Dirichlet, as I said. Instead of factoring over Z, which is quite naive, you take a suitable number field on which your equation can be factored. Of course, there are Diophantine equations on which you cannot factor at all. But sure. If you can, well, you do. And when you factor over number fields, you need to know a lot of things about the number field. You need to know the class number, the units. You need to know how prime numbers decompose in prime ideals. You need to know how to find generators of principal ideals when they are principal, and so on. And all this is now available at the click of the mouse on modern computer algebra systems, which wasn't at all the case. I mean, I say this for the students. I mean, when I was a student, it was completely inconceivable to do this kind of computations. I mean, I still remember people doing a PhD, and half of the PhD was computing the invariance of the suitable number fields that they needed. It was completely very hard work. Now it's stupid. I mean, you just click on your favorite computer algebra system and you have the answer in tenth of a second, at least if your number field is reasonable. So this part has completely disappeared. And so the use of number fields is absolutely essential, even though it's very classical. As I said, it was initiated by Fermat's last theorem, and it still remains one of the most powerful methods. Numerous applications and successes. So I already mentioned the use of Baker-type methods. More generally, there are methods which you can put under the title of Diophantine approximation methods. There are quite a lot of variants of this. Probably the most elementary is a method initiated by Runge's method, which is a very nice method. In fact, I also talked with René Schroff about this. He certainly knows much more about it than I do. All Diophantine equation methods, well, I will come back to this later, but all Diophantine equation methods boil down to a single stupid fact. If you take a real number whose absolute value is strictly less than 1, and which is an integer, it's equal to 0. Basic theorem. It sounds stupid, but of course, most of you are number theorists. You've met this theorem before, and it's really basic, and it gives you a really very powerful result. That's what Diophantine approximation is all about. But of course, the more sophisticated examples of Diophantine approximation are methods a la Baker, or more general. And finally, the most recent and certainly most spectacular methods are methods based on modular forms. So Ribot's theorem, Wiles' theorem, Taylor-Wiles, and so on, whose first and foremost success is the solution of Fermat's last theorem, of course, but it's more generally able to solve equations of the ABC type, A plus B equals C, where A, B, and C have restricted prime factors or are highly divisible by high exponents in them. And I must admit, well, I mustn't admit, I must insist on the fact that these modular methods, what really is important in these modular methods, and I think perhaps this is sometimes downplayed, is not at all Wiles' theorem. Of course, Wiles' theorem is probably by far the most difficult part of it. But okay, somebody had to prove this modularity conjecture, and Wiles did it with the help of Taylor, and then other people did it. But in fact, the only theorem you use to do to solve Diophantine equations is not Wiles' theorem. You need it, of course. You need to know that your elliptic curve is modular. But once you know this, the real theorem you use is Ribot's. So it's really Ribot that you use. It's not Wiles. I mean, you need Wiles to know that your curve is modular, but the theorem that you must use is the Ribot-Lower theorem. So I don't think that Ken Ribot needs any extra praise, but I would like to add to this the fact that in some cases, which are not that frequent, there is some magic going on. And this magic occurs essentially if the set of solutions of a Diophantine equation, of course, is set. It doesn't have any structure. But certain Diophantine equations have a set of solutions which does have a structure. For instance, the group of points of an elliptic curve, or the set of solutions of the Pelt-Fermat equation. More generally, if you look at norm equations, there is a structure, essentially a group structure. It doesn't have to be exactly a group. For instance, the invention by Shanks of what he called the infrastructure is absolutely beautiful. I mean, for those of you who don't know infrastructure, you should learn it. It's so nice. Shanks, of course, as usual with him, had extremely ingenious ideas, but presented it in a completely unreadable way. And the infrastructure was really cleared a little later after Shanks. But it's really very nice. So when you have structure in the set of solutions of Diophantine equation, usually you have magic with it. So in the case, well, here, of course, you know to solve a Pell equation, everyone knows that to solve x squared minus dy squared equals 1, you do continued fraction. Yes, but what some people in this audience maybe do not know is that this continued fraction has length square root d in average. And square root d can be pretty large. And that's where Shanks' infrastructure comes in. He explains how to compute this continued fraction expansion, what you need, the solution xy, in time much faster than square root d. And, well, okay, I call this a magical algorithm. You may or may not agree with me. But you find a solution by an algorithm. That's quite amazing. And the other example, of course, which is the one I gave as a student project, is the case of elliptic curves of rank 1 over Q. Now, just a reminder for, well, I guess everybody knows here about elliptic curves, but elliptic curves have, well, that's a tautology, rank 0, rank 1, or rank strictly greater than 1. And when I was young, people thought that maybe the proportion of higher rank curves was non-zero according to some computations made by Zaghi and other people, but it seems I've discussed with Mark Watkins and other people, now the belief is really that elliptic curves of higher rank form a zero proportion of elliptic curves. So you could say that essentially in nature about 50% of elliptic curves have rank 0, 50% have rank 1. If they have rank 0, there is nothing much to do. You need just to find their torsion subgroup, and that's algorithmic. So there remains elliptic curves of rank 1. And in that case, you have this magical algorithm called the Heegner point method, which is really extremely pretty. And I hope that the students will make a beautiful presentation of this method. But it's really, you can program it in a few hundred lines, and it just comes out like this. It's based, this construction of Heegner points is based, of course, on the theory of complex multiplication, which is also another magical fact in mathematics. I mean, when I learned, when I was a student, complex multiplication, I mean, the Kroneker's Jugendtraum, how can you create an algebraic number out of analytic functions? It's amazing. Of course, if you think of the exponential function, sure, it looks less amazing, but still, it's a beautiful theory. How am I doing in time? So let's start. So that was general introduction. So I start from the beginning. I'm sorry if this looks like tedious. I mean, it's a course after all, so I'm not giving a lecture. So let's start with local methods, and really the most naive local methods, working modulo powers of a prime. So I begin with really the most toy example possible, the equation x squared plus y squared equals 3z squared. Well, okay, you can read the proof. You just work mod 3, and you see that it's not possible. End of proof. Okay. Not very high level. I'm sorry for those students here who expect more, but okay, now let's go to a further equation. First case of Fermat's last theorem. Now, you all know, I guess, but I will repeat. Fermat's last theorem can be divided in two cases. The case where one assumes that x, y, and z are not divisible by the exponent. Well, the exponent can be assumed prime. And the case where it is. Now, this distinction is absolutely essential in the proof using algebraic number theory, a la Kummer. It's much less essential, although it does slightly exist in the proof of Wiles and Ribbit. But still, the name remains. So FLT1 for exponent 3 is the fact that x cubed plus y cubed equals z to the cube with 3 not dividing x, y, z is impossible. And here you simply work modulo 3 squared. And it just works. I could, of course, have given as many examples as possible of equations, for instance, where you have to work modulo 2 to the 4, 2 to the 5. It's completely artificial. I mean, you can play with Diophantine equations as long as you want. So in general, you need to use p-adic numbers, not just. So I apologize if this is well-known stuff to everybody, but still I decided to give this course at a, well, as self-contained as possible. So I remind you what you need to know about p-adic numbers. I'm not going to define p-adic numbers, I'm just going to tell you what you need to know about them. In addition to the fact, which I didn't write, that it's characteristic 0. That's absolutely essential. So, a homogeneous equation with integer coefficients has a non-trivial solution modulo all powers of p, if and only if it has a non-trivial solution in zp, or in qp, since it's homogeneous. That's one essential thing. So that's the reason for introducing p-adic numbers, is to put all congruences together. Second, there is a canonical integer valuation, Vp, and Vp of x is, of course, the exact power of p dividing x, whether x is rational or integral, it doesn't matter. And it satisfies the ultrametric inequality, Vp of x plus y, greater or equal to the minimum of the valuations, which is, of course, the cause of a very, the topology induced by this valuation is an ultrametric topology, which has rather strange properties if you've never met it, but I guess everybody has met it. One of the nasty things, well, it's very nice for certain respects, it's very bad for others, and one of the bad things is that it prevents you from doing analytic continuation, because if you take a circle of convergence of some power series, and if you take any point inside the circle of convergence, this point is itself the center with the same radius. So you just cannot extend in this way. There are other ways to do analytic continuation, but not that one. So the elements of QP with non-negative valuation are p-adic integers, so that's ZP, which has maximal ideal PZP. Invertible elements of ZP are p-adic units, those of 0 valuation, and you have a canonical decomposition, of course, of x into p to the VP of x times y with the p-adic unit y. Well, let's start with the bottom of the slide. Hensel's lemma, which is another name for Newton's method, says, well, there are many statements of Hensel's lemma, but the only case which I really need is the fact if you take a polynomial with coefficients in QP, and if you have an alpha in QP, which is some sort of approximation to a root. So the only thing we ask is that the valuation of f of alpha is at least equal to 1, and that the valuation of the derivative, that's very important, Vp of f prime of alpha is equal to 0. Then, simply by using Newton's method, it's completely elementary, there exists an alpha star, which is really a root of f of alpha star equals 0, and which is close to alpha. The valuation of alpha star minus alpha is at least equal to 1, and alpha star can be computed algorithmically, of course, using Newton's iteration. And as I already mentioned, testing local stability is easy and algorithmic. The last thing I need about p-adic numbers is the fact that power series can be used in quite a natural way, although some care needs to be introduced. If you take a rational number a, with non-negative valuation, and if the valuation of x is at least 1, then you can consider the power series 1 plus x to the a, and this power series converges. On the other hand, if the valuation of the exponent is negative, so if you have p in the denominator of a, then you need a stricter condition on the valuation of x. You need what I wrote. The valuation of x has to be at least the absolute value of valuation of a plus 1 when p is greater or equal to 3, a little more when p equals 3. And it converges to its expected value. Now, this is where you have to be careful. What I say here, for instance, if m is in z, then y is, if you take 1 plus x to the 1 over m, satisfies y to the m equals 1 plus x. That is true. However, you have to be careful of one thing. I'm sorry if I insult your intelligence. Probably everybody here knows what I'm going to say, but I still will say it. If you take, I don't know, some 1 plus, let's see, what example would I would have to indent this. 1 plus 7/9 to the 1/2. Yeah, that looks correct. 1 plus 7 over 9 to the 1/2. This probably converges in Q7 because of the 7/9. It also converges over R because 7/9 is less than 1. But it doesn't converge to the same value. Because over R, 1 plus 7/9 to the 1/2 converges to 4/3. And in Q7, it converges to minus 4/3. So you have to be careful. There are roots of unity cropping up everywhere in p-adic numbers. So, as an illustration, and I probably will finish, well, it depends how long I will take to do this. As an illustration of local methods, I would like to mention the problem of thermoaquartics. This is a problem which I discovered on reading a course by one of my colleagues from Paris. It's really Alain Krauss. It's really a very amusing subject because, well, maybe I shouldn't start with quartics after all. Most elementary Diophantine equations have lower degree than that. That is what one calls a curve of genus 3, and of course, the simplest Diophantine equations have genus 0, and genus 1, and so on. But still, I think it's one of the most amusing things, since in genus 3, really, nothing is known. You don't have any algorithms, nothing. So, I mean, for a specific genus 3 curve, you can try and work your way out, especially if the rank of the Jacobian is strictly less than the genus. Then you can do things using Chaboty, Coleman, and this kind of thing. But when you have a family of genus 3 equations like this one, there is no method. And that's why it's quite amusing, because in fact there are quite a lot of results which you can obtain on thermoaquartics. I will limit myself to the local problems, explaining how you do this, and refer you to my notes, to my book. It's not in the notes I put on the web, I think. Oh, maybe it is. For the detailed explanation of how you solve this equation globally, when you can solve it. Of course, there is no global solution to this equation. I mean, you can't say whether a number is a sum of 2 fourth powers. But still, you can solve this equation for many, many values of C. In fact, read the last line. The last paragraph. I'll only describe local solubility results. The global study involves many methods, so factorization in number fields, which is classical. Of course, you can factor x4 plus y4 in the field of 8th roots of unity, so that's very nice. You can also use coverings by elliptic curves. The Jacobian of this curve of rank 3, in fact, is a 3-dimensional abelian variety, of course, as any Jacobian of rank 3 curve, but in fact it splits as a product of 3 elliptic curves. So you can use coverings by elliptic curves. But even with all this data, you still cannot solve every possibility. You can go up to 10,000, although it's very difficult. By using the combination which I wrote here, you solve all but 4 cases up to 10,000. Then you have 4 values of C which are very resistant. I think the first one, which you cannot do in one of these ways, is 4,481. And there you really have to work extremely hard to show that the equation doesn't have any solution. Anyway, so let's denote by C the projective curve x4 plus y4 equals C. What can one say? So it's the curve C sub C, excuse me. There is a misprint. Well, here there is no misprint. The preceding page there is. So this curve is everywhere locally solvable. Here's the complete answer. As I said, it's usually completely algorithmic. And here is the answer is quite surprising because the numbers that occur seem to come out of the blue. So this curve is everywhere locally solvable, so has points in R and in QP. If and only if C is positive, of course, C has to be positive, otherwise it doesn't have any real solutions. And you need these congruences. So either C is congruent to 1 or 2 mod 16, so that's the solubility in Q2. For P dividing C not equal to 2, the primes have to be congruent to 1 mod 8. And then you have these strange congruences modulo 5, 13, and 29. C must not be congruent to 3 or 4 mod 5, 7, 8, or 11 mod 13, and this list of numbers modulo 29. Now, why? I mean, why 5, 13, and 29? Why just these 3 primes? I mean, it looks really strange because, I mean, we're just dealing with x4 plus y4 equals c. I mean, so apart from the fact that these 3 primes are congruent to 1 mod 4, that's about the only thing they have in common. Quite amusing to see why. So I'm not going to give the detailed proof. The proof is in the notes, but I'm going to explain the ingredients in the proof. First, if you want to look at the 2-adic solubility, then in fact you use this power series expansion that I mentioned a few slides before. You use the following fact, which is completely trivial, but still it's nice to use power series. The fact that the 2-adic unit x is a 4th power in Q2 if and only if x is congruent to 1 mod 16. It's a very elementary fact, but probably the most elementary way to see it is just to write x as 1 plus u and take 1 plus u to the 1/4 and to notice that this thing converges. And conversely, of course, if you take a 4th power, you can see that it's congruent to 1 mod 16. Okay, the second fact that you need is that if you take a prime which doesn't divide 2c and which is not congruent to 1 mod 8, then, in fact, the p-adic problem is, in fact, a simple problem mod p. C is a sum of 2 4th powers in QP, which is what you want to know, if and only if it is in FP. That's simply Hensel's lemma, but Hensel's lemma cannot be applied blindly. You need this condition that the derivative, equation of the derivative is equal to 0. So you can't lift any solution in FP to QP. You need some conditions, and these conditions are what I wrote here. P does not divide 2c and P not congruent to 1 mod 8. So you just need to look at the sum of 2 4th powers in FP. But now in finite fields, that's quite simple. You just look, use the pigeonhole principle, principe des tiroirs, and you see that if P is congruent to 3 mod 4, you cannot have any problem because any element of FP is a sum of 2 4th powers if P is congruent to 3 mod 4. And finally, probably the most important ingredient you use here is that if P does not divide 2c and P is greater or equal to 37, now the 37 well, I'll explain, then C is indeed a sum of 2 4th powers in FP. And this uses the Weil bounds, And the Weil bounds tell us that if you have a non-singular plane curve of genus G, then you know over a finite field, then you know precisely bounds for the number of points. Here the genus is 3, and you know that the number of points is at least equal to P plus 1 minus 6 square root P. 6 is 3 times 2. And this is strictly positive as soon as P is greater or equal to 37. Now, you can say these Weil bounds are not very easy. You need to prove the Weil bounds. Of course, there are elementary proofs, well, quote. But in this case, it's extremely simple because the equation is diagonal. And when you have diagonal equations, proving the Weil bounds is completely elementary. It just uses Jacobi sums. I mean, that's a very nice exercise, and in fact, that's how Weil started on this whole stuff. He started by proving the diagonal case, and then he generalized. Well, just generalized. That was, of course, enormous work, but here it's easy to prove. So, using all these ingredients, you get this theorem, because, of course, then you just have a few primes to look, and you see that the conditions that you need are exactly those. That's the solution. Okay, I will finish. I end at what? How many minutes? Oh, that's in 2 minutes. I think I can do it. So I will finish by showing you how local methods can apply to Fermat's last theorem. That's quite surprising because it's not in standard textbooks, but it's very elementary. So here is a statement, which I leave to you as an exercise. Fermat in QP. So there exist p-adic units, alpha, beta, and gamma, such that alpha p plus beta p equal gamma p. So FLT1, because I asked that they're units, is soluble p-adically. This is equivalent to the fact that there exist integers, a, b, and c, not divisible by p, such that the congruence modulo p squared is valid. And finally, this is equivalent to the fact that there exists an integer not congruent to 0 1, or minus 1 mod p with a plus 1 to the p congruent to the a to the p plus 1 mod p squared. This is an exercise, completely elementary first-year exercise. You just do congruences modulo p cubed and use Hensel's lemma to get number 1. This is really very simple. But as a corollary, you obtain something which I think is quite cute. If for all a between 1 and p minus 1 over 2, you have a plus 1 to the p minus a to the p minus 1 not congruent to 0 mod p squared, then FLT1 is true. And if you take your computer and compute this for a number of p's, you'll notice that this proves FLT, I mean, the first case of FLT, for quite a number of p's. I mean, it is not at all an empty condition, far from it. It proves FLT for very, very many p. It's quite amusing. And to finish today's talk, I just would like to mention, of course, if you take a equal 1, just 1, then you get 2 to the p minus 2. And if you divide by 2, p is odd, it's 2 to the p minus 1 minus 1. And using Eisenstein reciprocity, which is not at all a local statement, it's a global statement, you can prove that, in fact, a equal 1 is sufficient. It's called Wiefer's criterion. If 2 to the p minus 1 is not congruent to 1 mod p squared, then FLT1 is true for p. That's more complicated, and of course, the only known exceptions are 1093 and 3511. But even though this is more sophisticated, I would like to insist on the fact that this corollary which I give is also quite useful, even though less powerful, and it's just obtained by using local methods. Thank you for today.